what is the physical significance of period number and how this periodic table is classified, and we're going to study few periodic properties and its trend. Okay, very simple chapter but important too. Fine. So to start with, see, this is the rough outline of periodic table, right? Basically, how many elements are there in periodic table, or how many elements we have discovered so far?
Eighteen, 18 groups, ma'am.
Yes, this
18.
table, got 18 groups and
17 periods,
7.
ma'am.
See, in this table we have 118 types of elements, and these elements are arranged based on their atomic number. What is atomic number? Number of protons. Fine. So atomic number of hydrogen is 1. So hydrogen is placed in first period of the table or first row of the table, and second element is helium, third element is lithium, fourth is beryllium, fifth is boron, carbon, nitrogen, oxygen, fluorine, neon. So based on the atomic number, elements are arranged in this periodic table. Fine. And as Senthamil Chelvan said, we have 18 groups and 7 periods are there. See, actually horizontal rows are called periods. So we have 7 periods in periodic table, and vertical columns or groups, and we have 18 groups in periodic table. So this is period 1, this is period 2, this is period 3, 4, 5, 6 and 7. So totally we have 7 periods in this table, and there are 18 columns. This is column 1 or group 1, this is group 2, group 3 to 12 is placed here. This is group 13, 14, 15, 16, 17 and 18. So we have 7 periods and 18 groups. Okay. What is the physical significance of this period number and group number? What are all the stuffs we can understand from period number and group number? For example, lithium was placed in second period, right? So from this, what we can understand is period number always represents the valency shell of the element. So basically, the elements which are present in second row or second period will have the second shell as the valency shell. So period number represents valency shell and group number represents valency electron. For example, let us take this lithium. What is the atomic number of lithium? What is the atomic number of lithium? Atomic number of lithium. This is the third element. So atomic number of lithium is 3. What is the electronic configuration? It is 1s2, 2s1. So which is the valency shell, Kanna? What is the outermost shell of lithium? Whenever I'm asking about the valency shell, you have to check for the principal quantum number. So this is the principal quantum number, right? So the highest number is the outermost shell. So second shell is the valency shell, which means lithium is present in second period of the table. Okay, And as I've told you already, group number represents valency electron. So group 1 elements will have only one electron in its valency shell. And second group elements will have two electrons in its valency shell. And 13th group elements will have three electrons in its valency shell. In 13, this is the number which is present in one's place, right? So three electrons will be in the valency shell. And how about 14th group elements? 14th group elements will have 4 electrons in its valency shell. And 15th group element will have 5 electrons in its valency shell. 16th group elements will have 6 electrons. This is 7 electrons. And 18th group elements will have 8 electrons in its valency shell, but helium will have only 2 electrons because atomic number of helium itself is 2. So 2 electrons will be in valency shell. But rest of the inert gases will have 8 electrons in the outermost shell. Right? You're getting the point? Okay. What is the atomic number of sulfur? What is the atomic number of sulfur? Uh-huh. If it is 15, then that is phosphorus. Atomic number of sulfur. It is not 14. Silicon is 14. Yes, it is 16. So atomic number of sulfur is 16. So what is the electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p4. Kanna, what is the valency shell? What is the valency shell? Which is the outermost shell here. Audible now? Am I audible now? Can you hear me? Is my screen visible?
Yeah, now it is visible, madam.
So
Are
I've
you
written the electronic configuration of sulfur. So I've written the electronic configuration of sulfur. Could
are
you
you
please
able to
tell
see
me
the
which is the
screen?
valency shell?
Students, are you able to see the screen? Can you reply? நான் பேசுறது கேக்குதா? பூமிகா நான் பேசுறது கேக்குதாம்மா? நெட்வொர்க் இஷ்யூ மேடம். ஆக்சுவலாக முதல்ல கூட ஃபர்ஸ்ட் ஒரு 2 மினிட்ஸில் செந்தமிழ் செல்வன், ஆர் யூ ஏபிள் டு ஹியர் மீ? மேடம் நான்
Yes, sir.
பேசுறது கேட்குதா உங்களுக்கு?
கேக்குதுங்க சார். எனக்கு கேக்குதுங்க சார்.
ஆமா. செந்தமிழ் செல்வன் கேட்குதா?
Yes, sir.
கேட்குதா?
Yes,
கொஞ்சம்
sir.
ரிப்ளை பண்ணுங்க. சொன்னோன்னே உங்களுக்கு கேட்குதான்னு கேட்டால் உடனடியே ரிப்ளை பண்ணுங்க. ஓகே மேடம், கேரி ஆன். ஐ திங்க் தே ஆர் ஏபிள் டு
Okay,
கேட்க.
sir. Okay, sir. Okay. So, what is the valency shell of sulfur here? It is third shell, right? So, third shell is the valency shell. And how many valency electrons are there? How many electrons are present in third shell?
6, ma'am.
6 electrons. That's it. So from the electronic configuration, we can tell which is the valency shell and how many valency electrons are present in the atom. Similarly, we can tell the position of the sulfur also. Since the valency shell is third shell, definitely sulfur will be in third period, right? And could you please tell me the group number of sulfur? Here we have valency electron as 6 electrons, right? So could you please tell me the group number? From the valence electron, we can guess the group number. From the group number, we can guess the valence electron. So, what is the group number of sulfur? If group number is 13, then
16,
valency
ma'am.
electron will be, yes, exactly. So, since the valence electron is 6, group number will be 16. So, this is an oxygen family. Okay, so period number represents valency shell and group number represents valency electron. And similarly, a periodic table is classified into 4 blocks: S block, P block, D block, and F block. See, as far as sulfur is concerned, the last electron is entering into P subshell, which means sulfur is in P block. Here, as far as lithium is concerned, the last electron is entering into S subshell, which means lithium is present in S block. So, in this periodic table, group 1 and group 2 elements are S block element, group 13 to group 18 are P block element, and 3 to 12 are D block, and this is F block elements. Okay, so periodic table is classified into 4 blocks. These blocks are classified based on the electron, based on the subshell into which electron is entering, which means last electron is entering. Okay, fine. So now we're going to start with periodic properties and their trend. Okay, so what are the periodic properties you guys are familiar with? What are all the periodic properties you guys are familiar with? Definitely you have
Atomic
heard
radius,
about
ionic radius, ma'am.
very good. Atomic radius, ionic radius. Hmm. A very famous one is electronegativity, because you'd have come across this term in your organic chemistry also, right?
Yes, ma'am.
Electronegativity, electron affinity, effective nuclear charge, metallic nature, all these were periodic properties. Okay, so we're going to see the specific periodic properties and their trend here. So first one, which is effective nuclear charge. Now, what is nuclear charge? What is nuclear charge? The literal meaning. Nuclear charge is nothing but charge of the nucleus. What will be the charge of a nucleus? Will it be positive or negative? What will be the charge of a nucleus? Will it be positive or negative? What are all the subatomic particles which are present inside the nucleus? What are all the subatomic particles present in nucleus? Which is proton and neutron, right? So from atomic structure we know In atom, we have nucleus. Inside nucleus, we have proton and neutron, and electrons are revolving around this nucleus. And we know protons are positively charged, electrons are negatively charged, and there is no charge for a neutron. So I'm asking about the charge of nucleus. So inside nucleus, though we have proton and neutron, there is no charge for neutron. Protons are positively charged, so charge of the nucleus will be positive. Okay, and negatively charged electrons are revolving around the nucleus, right? Okay, let us take hydrogen. What is the atomic number of hydrogen? It is 1. So number of proton is 1 and number of electron is also 1. So now we'll consider only proton here. So since the atomic number is 1, we can understand that hydrogen got only one proton inside the nucleus. So what will be the charge of nucleus then? What will be the charge of nucleus? Since we have only one proton inside the nucleus, charge of the nucleus will be plus 1. Okay. How about helium? What is the atomic number of helium? It is 2. So number of protons will be 2. So what will be the nuclear charge of helium? Since we have 2 protons inside the nucleus, plus 2. Right. So how about lithium? Atomic number of lithium is 3. So number of protons is 3. So what will be the charge of the nucleus? It is plus 3. So number of proton represents the nuclear charge. Okay, could you please tell me for oxygen? What will be the nuclear charge of oxygen then? What will be the nuclear charge of oxygen? Yes, it is plus 8 because atomic number of oxygen is 8. So oxygen contains 8 protons. So it is plus 8. Okay, fine. So nuclear charge is nothing but your proton count. So proton count is nothing but your atomic number. So nuclear charge is nothing but your atomic number, which is represented with a character or an alphabet Z. Right. So now we are clear with the nuclear charge. Now we're going to understand what is effective nuclear charge. Let us take lithium. Atomic number of lithium is 3. So lithium contains 3 protons and of course 3 electrons. Right. Could you please tell me the electronic configuration of lithium? What is the electronic configuration of lithium?
1s2, 2s1, ma'am.
Yes. So the electronic configuration of lithium is 1s2 and 2s1. So this represents first shell of the atom contains 2 electrons and second shell got 1 electron, right? So as far as lithium is concerned, we have 3 protons inside the nucleus. So we know all the 3 electrons in this atom will be experiencing an attractive force from the nucleus, right? So these 2 electrons in the first shell will be experiencing an attractive force, which is basically the nuclear charge. And electron which is present in second shell also will be experiencing the nuclear charge. But what I want to know is which electron will be experiencing higher nuclear charge and which electron will be experiencing lower nuclear charge. Which will be experiencing lower nuclear charge from the nucleus or less nuclear charge from the nucleus? Or all the 3 electrons will be experiencing equal or same nuclear charge? Will it be same or different, Karna? See, as far as lithium is concerned, lithium got 3 protons inside the nucleus, right? And 3 electrons are present in the shell. 2 electrons are present in first shell and 1 electron is present in second shell. What I want to know is all the 3 electrons will be experiencing same attractive force from the nucleus or different attractive force from the nucleus. If it is different, which will be experiencing less nuclear charge or less attractive force? Kana, you guys are, you guys can understand the question.
Yes, ma'am.
So, which will be experiencing less attractive force from the nucleus? Will it be electron which is present in first shell or in second shell?
Second shell, ma'am.
Yes. What is the reason?
Shielding effect, ma'am.
Yes. So the first thing what we'll be thinking is the distance between the nucleus and the second shell is more. But not only the distance, as Sendamal Sheldon said, it is the screening effect, because here we have nucleus and here we have electron. This is the electron which we are considering, which is the valence electron, right? So between the valency shell and the nucleus we have inner shell, and in inner shell we have two electrons, and these two electrons will be revolving around the nucleus, and these two electrons will be shielding the nucleus. So uh, the electrons are shielded, I mean the nucleus is shielded by two electrons. So this valence electron will not be experiencing the complete nuclear charge from this system. So the original nuclear charge experienced by the valency electron is called effective nuclear charge. As far as lithium is concerned, the nuclear charge is 3, but the original nuclear charge experienced by this valency electron will be definitely less than 3, right? So effective nuclear charge is represented with the symbol Z star, that is equal to original nuclear charge minus screening constant. So this is the value which we can calculate, and there's a method called status rule, but we don't have that status rule part in your syllabus. But this is the formula to calculate effective nuclear charge, and effective nuclear charge is nothing but the original or actual nuclear charge experienced by the valence electron of the atom. Okay, you're getting my point? Any doubt?
Screening constant, ma'am.
Yes, it is screening constant, Kana. Yes, a screening constant. Shall we proceed?
Yes, ma'am.
Okay. So now we understood what is nuclear charge and effective nuclear charge. Now we're going to see the trend. That is, as we move from left to right in a periodic table, what is happening to nuclear charge, and as we move down the group, what is happening to the nuclear charge. Okay. So let us take a group 1 element. Group 1 element is lithium, sodium, potassium, rubidium, cesium, and francium. So atomic number of lithium is 3, sodium is 11, and potassium is 19. Electronic configuration of lithium is 1s2, 2s1. As far as sodium is concerned, electronic configuration is 1s2, 2s2, 2p6, 3s1. So in lithium, the valency shell is second shell, and inner shell got 2 electrons, right? So these 2 electrons will be shielding the nucleus. So remaining nuclear charge will be only the remaining nuclear charge will be experienced by the valency electron. As far as sodium is concerned, this is the valency shell. And how many inner electrons are there in sodium? How many inner electrons are there in sodium?
10 NL.
10 inner electrons, right? So if you compare the inner electrons of lithium and sodium, sodium got more number of inner electrons, so shielding will be more in sodium. So now tell me which valence electron, whether it is lithium's valence electron or sodium's valence electron, which will have highest effective nuclear charge?
Lithium, ma'am.
Yes, because inner electron is lesser in lithium, so shielding will be less in lithium. So valence electron which is present in lithium will be experiencing more nuclear charge than sodium. So what we can conclude is, as we move down the group, effective nuclear charge decreases. Okay, so effective nuclear charge left to right in a periodic table and top to bottom in a group. So as we move down the group, effective nuclear charge decreases, right? Because inner electrons are getting increased as you move down the group. Now we'll see about the trend as we move left to right in the periodic table. So let us take this second period element. So second period elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Atomic number of lithium is 3. This is 4, 5, 6, 7, 8, 9, and 10. So number of proton is 3. Number of electron is also 3. As far as beryllium is concerned, number of proton is 4. Electron is also 4. Proton 5, electron 5. Proton 6, electron 6. 7, 8, 9, and 10. Okay, so let us write the electronic configuration of all the elements. For lithium, it is 1s2, 2s1. For beryllium, it is 1s2, 2s2. For boron, 1s2, 2s2, 2p1. This is 1s2, 2s2, 2p2. This is 1s2, 2s2, 2p3. This is 1s2, 2s2, 2p4. This is 1s2, 2s2, 2p5. This is 1s2, 2s2, 2p6. Kana, listen here. As we move from left to right in a periodic table, proton count is increasing, which means nuclear charge is increasing. Similarly, electron is also increasing, but the extra electrons are added into the same shell, which is second shell here. So as we move from left to right in the periodic table, since proton count is increasing, nuclear charge is increasing, but there is no changes in the inner electron count. See, all the elements got only 2 electrons in the first shell, right? Whenever we are adding the electron, it is getting added to the second shell only and not on the inner shell, right? So as you move from left to right in the periodic table, there is no change in the number of inner electrons, but there is an increase in the nuclear charge. Now tell me, if you move from left to right in the periodic table, what will happen to the effective nuclear charge? Will it get increased or decreased? There is no changes in the inner count of inner electron, but nuclear charge is getting increased. So now tell me, as we move from left to right in a periodic table, obviously effective nuclear charge will get increased. So left to right in a periodic table, effective nuclear charge increases because there is no change in the number of inner electrons, but there is a significant increase in the nuclear charge. And as you move down the group, number of inner electrons are getting increased significantly, because of which shielding is getting increased. So effective nuclear charge is getting decreased. That's it. So effective nuclear charge is very important, because based on this periodic property, we're going to derive the rest of the periodic properties. Okay. So the next property which we're going to discuss is atomic size. Atomic size, or this can be related with the radius of the atom. What is the atomic radius?
The distance
What
between
is?
the nucleus and the valence electron, ma'am.
Yes, distance between the center of the nucleus to the valency shell. This is first shell. Let us say this is the second shell. So distance between the center of the nucleus to the valency shell is the radius. Okay. Now, Hannah, if effective nuclear charge is more, what it mean? The valency electron is experiencing higher attractive force or more attractive force from the nucleus. So if effective nuclear charge is more, then this valency electron will be experiencing more attractive force from the nucleus. So what will happen to this electron? It will move towards the nucleus, right? So what will happen to the radius or the size of the atom? Since the valency electron is moving towards the nucleus, then what will happen to the radius of the atom? Will it get increased or decreased? If the
Decreases,
valence
ma'am.
electron, yes, the valence electron is getting or experiencing higher attractive force from the nucleus, so this electron will be moving towards the nucleus, so distance between the center of the nucleus and the valency shell will get decreased. So effective nuclear charge is more, then radius will be less, so they are inversely proportional. So now tell me, as you move from left to right in a periodic table, effective nuclear charge increases, so radius of the atom will get decreased. Okay, as you move down the group, effective nuclear charge is getting decreased, so atomic size or radius will get increased. That's it. Now we'll see all the periodic properties and its strength, and after which there are few nuances in each properties that we'll discuss later. Okay, so this is the second periodic property, which is atomic size or atomic radius. Okay, any doubt? Any doubt, Kana?
No, ma'am.
Fine. So now we'll move on to third third atomic property or periodic property, which is called ionization energy. Ionization energy, or it is also called as ionization enthalpy, or it is also called as ionization potential. Hannah, what is ionization energy? This we have already discussed in atomic structure also.
Ma'am, the minimum energy required to remove the last electron, ma'am.
Very good. So minimum amount of energy required to remove a loosely bound electron, which is your valence electron, from an isolated gaseous atom. Okay. See, let us say A, which is a which is an isolated gaseous atom. I want to remove a valence electron from the I have to remove the electron from its valency shell. Have to do that. Have to do that, Kana. See, this is the nucleus. This is the first shell and this is the second shell. Let us say this is the valence electron. We know that all the electrons are attracted towards the nucleus. So this electron also will be experiencing an attractive force from the nucleus, right? And what we have to do to remove this electron, we have to break the attractive force between the nucleus and the valence electron. So to break the attractive force, we have to supply a particular amount of energy on this electron, and that energy is called ionization energy. So minimum amount of energy required to remove this valence electron from the isolated gaseous atom is called ionization energy. So if you supply a particular amount of energy, by observing this particular amount of energy, electron will be ejected out. And what will be the charge on this atom then? Will it be positive or negative?
Positive, ma'am.
Yes, it is positive, because in this neutral atom, number of proton and electron will be same. For example, if proton count is 11, then electron count will also be 11. So this contains 11 positive and 11 negative charge. So initially charge will be 0. It was a neutral system. But after removing an electron, there will be 11 positive charge and just 10 negative charge. So there will be 1 positive charge on the atom. So now this atom was converted into a cation, and minimum amount of energy required for this conversion is called ionization energy. Okay, right. See, whenever you're supplying a particular amount of energy to the system, then that should be represented with the positive sign. Whenever the system is releasing a particular amount of energy, then that has to be represented with negative sign. So as far as ionization energy is concerned, we are supplying energy to the system, so it will be positive. So whenever you are representing ionization energy, the quantity has to be represented with positive sign. And of course the unit will be, see here we are talking about energy, so the unit will be the unit of energy, so it is kilojoule per mole or kilocalories per mole. Okay, so this is ionization energy. Now we'll talk about the relationship between ionization energy and the effective nuclear charge. Kana, could you please tell me how this effective nuclear charge is related to ionization energy? Is it directly proportional or inversely proportional? And what is the
Inversely, ma'am.
justification? Okay. So what you mean is if effective nuclear charge is more, then ionization energy is less.
No, ma'am. Directly
That was your
proportional,
point,
ma'am.
right? Okay. So now it is okay. Now you're telling me it is directly proportional. Okay, fine. We'll see which is right. See, if effective nuclear charge is more, then what it mean? This valence electron is experiencing more attractive force from the nucleus. So this electron is strongly bounded towards the nucleus. Now it is really difficult to remove this electron. So to remove this electron, we have to supply more amount of energy to remove, because we have to supply more amount of energy to break the attractive force between the nucleus and the valence electron. So if effective nuclear charge is more, that is if the electron is experiencing more attractive force from the nucleus, then definitely we have to supply more amount of energy to remove it. Okay, so effective nuclear charge is directly proportional to ionization energy, so they are directly proportional. Now could you please tell me the trend as we move from left to right in a periodic table? Effective nuclear charge increases, so ionization energy also increases. As you move down the group, as you move down the group, as you move down the group, what is happening to effective nuclear charge? What is happening to effective nuclear
Decreases,
charge
ma'am.
as you? Yes, it decreases. So, what is happening to ionization energy then?
Decreases, ma'am.
Yes. Now we'll see a question. Could you please answer this question? The correct order of decreasing first ionization potential is? In each option, there is a particular order for ionization potential. They are talking about four elements: potassium, rubidium, cesium, and calcium. So, based on the position of these elements in the periodic table, we have to arrange these elements based on its ionization potential. So first, please place these elements in the periodic table and try to crack this question. If you want any clue, please let me know. I'll give you a clue. Or at least I'll tell you the position of these elements. Okay. Sendamil
Option
Chelvan's
B,
answer
ma'am.
is second option. Okay. How about Bhumika and rest of the students? Sendamil Chelvan, can you please reconsider your answer, Kana? They're talking about group 1 and group 2 elements. Please write all those elements in uh, group 1 and group 2 and find the order. Okay, now the children's answer is option C. Okay, we'll check now. Okay, I'll give you the elements in group 1 and group 2. What is the first element in first group? Lithium, sodium, potassium, rubidium, cesium, and francium. In group 2, elements are beryllium, magnesium, calcium, strontium, barium, radium. Okay, so the elements what they're talking about is calcium. Where is calcium? Is here. Rubidium, cesium, and potassium. Now tell me the order. We know as we move from left to right in the periodic table, ionization energy increases, and as you move down the group, ionization energy decreases. That is a clue. And I've given you the position also. Now tell me the right order. Okay. Now send them children's answers option A. We'll check now. Bhumika.
Ma'am, option A, ma'am.
Okay, option A. We'll check now. See, as we move from left to right in a periodic table, ionization energy increases. So, which is the rightmost element? Calcium. So, calcium will have the highest ionization energy. So, second and fourth option were ruled out. So, as far as group 1 elements are concerned, we have potassium, rubidium, and cesium. As you move down the group, um, ionization energy decreases. So, cesium will have the lowest energy. So highest is calcium and lowest is cesium. So answer is first option. Okay, fine. You're getting my point? Any doubt? Okay. Sandra Michelvan, can you please read this question? You just read this question. What is the question? The correct order of decreasing first ionization potential. And now, what is this first ionization potential? What is mean by first ionization potential? Till now we have been discussing about just ionization potential, right? Or just ionization energy. What is this first ionization energy? Okay, we'll see that now. Okay, I have an atom which is in gaseous state, and let us say a number of proton. I'm just writing the hypothetical number. So let us say the number of proton count is 13. So what will be the electron count? If proton count is 13, what will be the electron count? It will be 13 again, right? For any neutral atom, proton and electron count will be same, right? Now I'm going to supply a particular amount of energy to remove the electron. So after removing the electron, there will not be any change in the proton count. So still it is going to be 13. What will be the electron count? After removing one electron, what will be the electron count? What will be the electron count? Initially it was 13 electron. After removing one electron, that will be only 12 electrons. So what will be the total charge on the species now? +1, right? Now the amount of energy required to remove the first electron in an atom is called first ionization energy. Okay, now I have a cation and to which I'm supplying a particular amount of energy to remove the second electron. So proton count will still the same. It will be 13 plus. But what will be the electron count now? It will be 11. So what will be the total charge? It will be 2 plus. So the amount of energy required to remove the second electron from a cation is second ionization energy. Now I'm going to supply a particular amount of energy to remove the third electron. So this is 3 plus. So proton count will be same, electron count will get reduced. Okay. So the amount of energy required to remove the first electron is called first ionization energy. Energy required to remove second electron is called second ionization energy. To remove third electron, that is third ionization energy. Okay. So these ionization energies are called successive ionization energies. Successive ionization energies. So ionization energy 1, ionization energy 2, ionization energy 3, and so on. Now I want you to tell me which will have the lower value and which will have the higher value. Among first, second, and third ionization energy, which will have highest value and which will have lowest value? Is it ionization energy 1, 2, or 3? Which will have the highest value? What is first ionization energy? Amount of energy required to remove the electron from an atom. What is second ionization energy? Amount of energy required to remove an electron from positively charged system. Okay, which is easy and which is difficult? Initially the system got 13 protons and 13 electron. So 13 protons are holding this 13 electron. I've supplied a particular amount of energy to remove one electron. Now we have 13 protons and just 12 electrons. So this 13 protons will be holding the electron so tight. So to remove an electron from this 12, I mean to remove the electron from the system is really difficult, right? Because this 13 protons will be holding the electron so tight. So the amount of energy required to remove the electron from this system is really difficult, right, Kana? But how about in this system? See here we have 13 protons and very few electrons. We have just 11 electrons. So here electrons will be attracted towards the nucleus so tight. So removing that electron is also very difficult. Now tell me which will have the highest energy and which will have the lowest energy. As electron count is getting increased or as proton count is getting increased, what is happening to the ionization energy? It is getting increased, yes. So value of first ionization energy will be lesser than second one, and value of second ionization energy will be lesser than third one, and so on. Okay, so this is the general order. Okay. Now um, in a question they'll give you the successive ionization energies and they may ask us to find which elements ionization energies are that. Okay, we can find that. See, for example, mm, magnesium. What is the atomic number of magnesium? From the values of ionization energy we can guess the element, or at least we can guess the group in which that element is present. So what is the electronic configuration of magnesium? It is 1s2, 2s2, 2p6, 3s2, right? Okay. Now I'm going to supply a particular amount of energy to remove the electron present in 3s. Let us say the value is 500 kilojoule. Okay, this is the first ionization energy. And now magnesium will get converted into magnesium plus. Now I'm going to supply a particular amount of energy to remove one more electron from 3s. So definitely value will be greater than 500, say 900 kilojoules. Okay, of course there will be, uh, of course we have to supply more amount of energy to remove the second electron for obvious reasons. Okay, now I have to remove the third electron. See, which is the third electron here? First electron was in 3s orbital. Second electron was also in 3s orbital, right? How about third electron? Where the third electron is present?
2p, ma'am.
Very good. So 2p. See, initially the electron is present in third shell, which is the outermost shell. So removing electron from third shell was uh, relatively easy. But now we have to remove the electron from inner shell. So definitely amount of energy required to remove the electron from inner shell will be more. It will be significantly more. It is not the difference of 200, 300 and all. The difference will be very huge. For example, it may be around 5000 kilojoule. See, there is a huge jump, right? So the jump is between second ionization energy and third ionization energy. So from this, what we can understand is this element got only 2 electrons in its valency shell. Okay, so the amount of energy required to remove the electron from valence shell is relatively lesser than the amount of energy required to remove the electron from the inner shell. So from the jump, we can understand how many valence electrons are present in the atom, and from the valence electron, we can find the which in which group that element is present. Okay, you're getting my point. If the jump is between first and second ionization energy, then the number of valence electron will be 1. If the jump is between second and third ionization energy, the number of valence electron will be 2. If the jump is between third and fourth ionization energy, the number of electrons will be, that is number of valence electrons will be 3. If number of valence electron is 3, then that element is from 13th group. If the element got 2 electrons in its valency shell, then it is from second group. As simple as that. Okay. Now I'll give you a question. I want you guys to crack that. So the question is, okay, here is the question. They have given you the successive ionization energies, and from the values of successive ionization energy, we have to find uh, the group in which that element is present. Okay. Bhumika, what is the answer? Ritwan,
Ma'am, for A, ma'am.
Ye. Could you please justify the answer? Okay. The successive ionization energies are 520, 8000. See, here there is a huge jump between first and second ionization energy. So what it means? The element got only 1 electron in its valency shell. If the valence electron is 1, then the element is present in group 1. So answer is first option. So Sendamil Chelvan's answer and Bhumika's answer is right. Okay. I have another question. What is the answer for this question, Kana? The first ionization potential is maximum for which of the elements?
Nitrogen, ma'am.
Nitrogen. Justification, Kana? Why nitrogen and why not oxygen?
Ma'am, nitrogen வந்து ஆஃப் ஃபீல்டு கான்ஃபிகரேஷன் மேம்.
Hmm.
So it is more stable, ma'am.
Okay, right. See, till now we have been discussing only the trend of ionization energy. As you move from left to right in the periodic table, ionization energy decreases, and as you move down the group, ionization energy decreases, right? So this is what the normal trend. But apart from the general trend, we have to check few other factors also to find the exact ionization potential. Now we'll see the factors influencing ionization potential. One of the factors is half-filled and completely filled configuration, as Senta Mitchell said. See, we have four elements here, which is boron, beryllium, nitrogen, and oxygen, and they are basically the second period element. So elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And the elements what they are talking about is boron, nitrogen, oxygen, and beryllium. So we know that as we move from left to right in the periodic table, rightmost element will have the highest effective nuclear charge and highest ionization potential. But the actual answer is nitrogen, because see, the electronic configuration of oxygen is 1s2, 2s2, 2p4, and for nitrogen it is 1s2, 2s2, and 2p3. Though the effective nuclear charge is greater for oxygen, the electronic configuration of nitrogen is a half-filled configuration. Whenever we are encountering this kind of half-filled or completely filled configuration, they are considered to be the most stable one. So removing electron from this most stable configuration is really difficult. So we have to supply more amount of energy to remove the same. So though oxygen got highest effective nuclear charge, nitrogen will have the highest ionization energy because of its half-filled configuration. So half-filled and completely filled configuration is one of the parameters we have to consider while selecting, or we have while we are ordering the elements based on ionization energy. Okay, so we'll see what are all the factors which influences ionization potential. First factor is effective nuclear charge that we have discussed already. If effective nuclear charge is more, ionization energy is more. How about size? How the size of the atom and ionization energies are related? How the size
Inversely,
of the
ma'am.
atom? Yes, if the atomic size is less, then the distance between the nucleus and the valence electron is less. So the valence electrons are strongly attracted by the nucleus. So we have to supply more amount of energy to remove the same. So smaller the size, higher will be the ionization energy. So they are inversely proportional. Okay. Next parameter. Hannah, if the electron is present, I have two systems. In first system, the electron is present in third shell. That is, your valency shell is third shell. In second system, the electron is present in fourth shell. From which system we can remove the electron very easily? In first one or in second one? From where we can remove the electron easily, or for which the ionization energy will be less?
Fourth shell, ma'am.
Very good. Because distance between the nucleus and this fourth shell is more. So the attractive force experienced by the valence electron will be less. So it is easy to remove, right? Okay, this is about shell. How about subshells? If the electrons are present in S subshell, in other system electron is, see, in both the cases the electron is present in third shell. As far as subshell is concerned, in first system, electron is present in S subshell, and in another system, electron is present in second subshell, from which we can remove the electron easily, or for which the ionization energy will be less. Sorry, Kanna.
Ma'am, it is easy to remove from p orbital, ma'am.
Very good. From P subshell, because among S and P subshell is quite far from the nucleus, right? So as far as subshells are concerned, it is really difficult to remove the electron from P subshell, S subshell, then it is P, then it is T, and finally F. If the electron is present in F subshell, it is really easy to remove because it is very far from the nucleus. Okay. How about inner electrons? How about inner electrons? The electron is present in inner shell. If number of inner electrons are more, then these inner electrons will be contributing for shielding. So nucleus cannot hold the valence electron. So removing that kind of valence electron will be easy. So number of inner electron is more, then ionization energy will be less. They are inversely proportional. Okay. And fifth point, which we have discussed already, half filled and completely filled configuration will have highest ionization energy. Okay. Now we'll talk about three elements: lithium, beryllium, boron. Atomic number 3, 4, and 5. Could you please arrange these elements in terms of ionization energy? Which will have highest ionization energy and which will have lowest ionization energy?
Beryllium and lithium, ma'am.
Which will have higher one and which will have lower value, Kanna?
Beryllium higher, ma'am. Lithium lower, ma'am.
Okay. Why so?
Beryllium has completely filled state, ma'am.
Okay.
So it has more stability, ma'am. So it requires more energy to remove the valence electron, ma'am.
Okay. So you're telling me that as far as beryllium is concerned, that got completely filled configuration. So removing electron from completely filled configuration is difficult. Am I right?
Yes, ma'am.
Okay, fine. So could you please tell me the order? You have to arrange these elements in particular order. Either it can be increasing or decreasing. Okay. Listen here. Can I listen here? See, what is the general trend as far as ionization energy is concerned? As we move from left to right in a periodic table, ionization energy increases. So what we'll be expecting is lithium will have the lowest ionization energy because this got very least effective nuclear charge, after which beryllium, and after that boron. This is the expected ionization energy order, but actually it is wrong. We'll see the justification, or we'll see the right answer. See, as far as the lithium is concerned, the atomic number is 3. The electronic configuration is 1s2, 2s1. For beryllium, it is 1s2, 2s2. And for boron, it is 1s2, 2s2, and 2p1. See, lithium is in the leftmost corner of the periodic table. So lithium will have the very less effective nuclear charge. So ionization energy will be least for lithium, no doubt about it. But as far as beryllium and boron are concerned, here the valence electron is present in S subshell. Here the electron is present in P subshell. Tell me from which subshell we can remove the electron easily. Is it from S subshell or from P subshell? From which subshell we can remove the electron easily, which will have lesser ionization potential?
Lithium, ma'am.
Karna, lithium is different. Yes, lithium got lesser effective nuclear charge, that got lowest ionization energy. But now I'm comparing beryllium and boron.
Boron, ma'am.
Yes, because boron's valence electron is present in p subshell. P subshells are quite far from the nucleus, so removing electron from p subshell is easy. So after lithium, boron, and definitely beryllium will have the highest ionization energy. The reason is here the electron is present in s subshell, and here the electron is present in p subshell. Okay. But Centaur Shelvin, you told me in beryllium's configuration, the system is completely filled, but that is not the case. Actually, half filled and completely filled configurations are more stable because of its exchange energy. See, whenever we are talking about p subshell or d subshell, in p subshell we have three degenerate orbitals. And as far as d subshells are concerned, we have five degenerate orbitals. Whenever you are filling these degenerate orbitals, there is exchange possible because of exchange energy, because of exchanges. There is a particular amount of energy which is getting released, which is called exchange energy, right? But this exchange energy is possible whenever we have degenerate orbitals. In p subshell, d subshell, and f subshells, we have degenerate orbitals. But as far as s subshell is concerned, we have only one orbital. So there is no exchange possible. So you cannot claim a half filled or completely filled configuration for s orbital. Okay. So, but here we can talk about the distance between the nucleus and the s, and distance between the nucleus and the p. Okay. So you have to justify the answer based on the penetration effect and not the half filled and completely filled configuration. You're getting my point, Kana?
Yes, ma'am.
Right. Your answer is right, but justification has to be like this. Okay, so this is the right order. So here the answer is penetration effect. Here p subshells are quite far from the nucleus, so removing electron from p subshell is easy. So boron will have the lesser ionization energy than beryllium. Fine. Now we need to compare carbon, nitrogen, oxygen. Atomic number is 6, 7, and 8. The expected order is as we move from left to right in a periodic table, ionization energy increases. So carbon, nitrogen, and oxygen. But we know this is the wrong order because the electronic configuration of nitrogen is 1s2, 2s2, 2p3. Here it is 1s2, 2s2, 2p4. So carbon is the leftmost element. So carbon will have the lesser ionization energy. There is no doubt about it. But as far as nitrogen and oxygen is concerned, though oxygen got higher effective nuclear charge, the configurations are just partially filled configuration. But as far as nitrogen is concerned, this got a half filled configuration because of exchange energy. Nitrogen is more stable. So from stable configuration, it is difficult to remove electrons. So ionization energy will be highest for nitrogen. So this is the right order. Okay. Any doubt? Okay, fine. Right, Kanna. So we'll move on to next periodic property, which is called electron affinity. Or they may use this term also, electron gain enthalpy. What is electron affinity, or what is affinity basically? Affinity is nothing but attraction towards electron. Okay, I have an isolated gaseous atom to which I'm trying to add one electron. If this atom gains one electron, then it will get converted into anion. And what will be the charge on this system? Since it is gaining only one electron, this will have only one negative charge. Okay. So, if an atom accepts one electron so happily, then that system or that atom got higher electron affinity. Okay. So, how this is possible? If the system got higher effective nuclear charge, then that nucleus is so strong which can hold the valence electron so tight. So in that kind of system, adding one more electron will be easy. So if the system got higher effective nuclear charge, then electron affinity will be more. Okay. Now we'll talk about this electron gain enthalpy. It is just the opposite of ionization energy. See, as far as ionization energy is concerned, we are supplying a particular amount of energy on the electron and we are removing it. But here we are adding one electron. An atom, after gaining one electron, it is releasing a particular amount of energy that is called electron gain enthalpy. If a system got higher effective nuclear charge, then that system got more electron affinity. So that atom can gain electron so easily, which means the electron gain enthalpy will be more. And as I've told you already, if the system is releasing an energy, a particular amount of energy, then that has to be represented with negative sign. So as far as this atom is concerned, it is gaining one electron and it is releasing an energy. So electron gain enthalpy will be negative. Okay. If electron affinity is more, then that will release more amount of energy. So value will be more negative. Okay. So adding the first electron to an isolated gaseous atom is easy. Okay. Now we'll talk about the trend. As I've told you, effective nuclear charge is directly proportional to electron affinity. Now could you please tell me the order or the trend? As we move from left to right in a periodic table, what will happen to the electron affinity? As we move from left to right in a periodic table, ionization, effective nuclear charge is more. If effective nuclear charge is more, then electron affinity also will be more. As we move down the group, effective nuclear charge is getting decreased, so electron affinity will also get decreased. So this is the order. Okay, fine. Now, as successive ionization energies, we have successive electron affinities as well. See, it is a isolated gaseous atom. For example, this contains 8 protons and it will have 8 electrons also, right Kana? Now we are adding one electron to it. So what will be the proton and electron count? What will be the proton and electron count? We are adding only one electron to that. So proton count will be same. How about electron count? It will be 9. So the charge on the atom will be -1. Right. Now we going to add one more electron to the system. See, this is electron affinity 1. Now I'm going to add one more electron. Is it really possible or is it really easy? See, here there are 12 protons. It is holding 12 electrons, which is easy. But here there are only 8 protons and 9 electrons. Already the electron count is more. Now we are adding one more electron to it, which is